Welcome to Lecture 2. In this lecture, we're going to work on the electric fields around continuous charge distributions.
Electric fields of point charges and groups of point charges were pretty well covered in Physics 1051. Now, of course, not everything is a point charge. The image on this slide is of electric eels. They have electric field lines around them, and they use those electric fields to know where they are and to communicate. We're going to get going on how to find electric fields of continuous charge distributions around charged objects of different shapes. Let's do a recap of the 1051 approach. If we had 7 discrete charges, and I have them drawn here, 1 through 7, we wanted to find the total electric field at point P right here. What we would do is we would draw the electric field vectors due to each one of these 7 charges. I'm going to try and do that here now. So my electric field due to Q1 at point P starts at point 1 and starts at point P and goes away from charge 1. There's my electric field due to charge 1. I'm going to do 7 next. My electric field due to charge 7, since charge 7 is positive, it's going to point right away from charge 7. There's my E7. Whoops, I wanted to make my 7 look like a Z. Okay, let's do charge 2 next. My electric field due to charge 2 is positive. I'm taking that all of these charges are identical, same magnitude, same sign. So the electric field E2 points away from it. Let's do 6 next. So E6 points away from it. Let's do 3 and 5 next. Electric field E3 starts at P and points away from charge Q3. Electric field due to Q5 starts at P and points away from 5. And then our last charge is due to Q4, which starts at P and points away from it. Okay, so there's 7 electric field vectors. My goodness, I said 7, so I wrote 7. There's the electric field due to charge 4. Now we have 7 electric field vectors, and the net electric field would be the vector sum of each of these fields. So our total electric field is the sum of each individual electric field, and that's definitely a vector. We'd have to think about components. Let's look at our components for a moment. Each of these electric fields, 1 through 7, they all point to the right. So my x components are all going to add up. How about my y components? Well, my charges are symmetrical up and down. So 1 and 7 are the same distance away from 7, from the midpoint. So 1 is a certain distance above the midpoint, 7 is the same distance below. That means E1 and E7 have the same length, but E1 points down and E7 points up. That means that the y components of E1 and E7 cancel. And that's also true for 2 and 6 and 3 and 5. And they cancel due to symmetry. We're going to use this symmetry idea quite a bit as we do the electric fields due to charge distributions. So our total electric field is going to be all in the x direction, and it's going to point to the right. So our net electric field is all of these vectors added up, and it will look something like this. There's our net electric field at point P, due to 7 discrete charges. Next, let's confirm that with a PhET simulation. So I popped over to the PhET simulation. Here's how you find it if you want to try it for yourself. I put in 7 positive charges. I put a point P some distance away from that middle charge, and we see that it does indeed point to the right. Some of the stuff you might notice is that up around here at the top it curves out a bit, curves down a bit here. So we found the electric field some distance away from the middle, and what we found here in our ideas matches what we found in the simulation. We're working towards a continuous charge distribution, which means not discrete charges. These are all very individual. You can see each charge. So how do we make a continuous charge distribution? Well, we can take these 7 charges and we can push them closer together. It still looks kind of like discrete charges. We can see the little individual charges, but they are closer. It looks more like they're together. We apply the same process of drawing each of the electric fields. We'll see that each of the y components cancel, and our net electric field still points to the right. So our net electric field is still the sum of each of the individual fields, and our answer points to the right. Okay, now we want to make it a true continuous distribution of charge. For a true continuous charge distribution, we mean something like a line of charge, like a wire. So this is a continuous charge distribution right here. To make a continuous charge distribution, we finish what we started on the previous slide, but now we take many, instead of just 7, we take many very small charges and push them close together. That's what makes our line of charge. Let's see if we can draw a few of those on the picture. So we would take many small charges, and they're all pushed really close together. So we make the charges very small. And very small is important enough to go in capital letters. And very close together. When we had our discrete charges, they were individual charges. When we have many charges and they're very small, instead of an individual charge, we give it a notation of dq. So this is a math notation. This is one individual discrete charge. dq means a very small amount of charge, a little bit of charge. The d and the q go together. There's one symbol altogether. Okay, for our net electric field, when we had our discrete charges, the net field was to the right because the y components canceled. So the net electric field was the sum. We only had to add up the x components because all the y's canceled and it pointed to the right. When we do an integral, or sorry, when we find the electric field due to this line of charge, the field is still going to be to the right because the y components are still going to cancel. But now when we do our sum, since it's an electric field, due to many teeny tiny charges, means we're going to get a sum of many teeny tiny electric fields, and the sum of many teeny tiny things is an integral. So instead of the sum symbol, we put the integral symbol. Instead of EX, we put a DE for small bits of electric field, and it still points to the right. Okay, this is our idea. For a continuous charge distribution, we have many small charges. We're still going to find the little bits of electric field, the individual electric fields, and we're still going to add them up, but now that addition is called an integral. So this is where we're going with this. So just before we get into the mathematics of calculating the electric field due to the continuous charge distribution, here's our PhET simulation again. On the left, we had our 7 discrete points and our electric field. Here, now on the right, we have many charges pushed together, and we have our electric field points to the right again. The field is actually so big it goes straight off the screen, so I can't get the whole thing in here. As you look at this, you notice there's maybe more curvature right here and less right here. If we could get to a truly infinitely long distribution of charge, we would see that all those lines would be straight, and we'll get there in our workings and we'll show that that's true.